Let us just first write the binomial coefficients. Since this is fourth power, so this is 4c 0, a to the power 4, b to the power 0, plus 4c 1, a cube b, b to the power 1, plus 4c 2a square b square, plus 4c3 a to the power 1 b cube, plus 4c4 a to the power 0 b to the power 4. Okay, and now we write them as a summation. Since we have already seen the technique for writing this summation, here also we try to find that same thing. Here also the same thing is happening. You see, exponent of b is the same as this number, 1, 1, 2, 2, 3, 3, 4, 4. So we straight away write summation I, in this case, okay, let's just write I afterwards, 4c, I mean this limit afterwards, 4ci, because we have 4c0, 4c1, so I is varying from 0 to 4, 4ci, b to the power I, a to the power, the sum of these two exponents should become 4. So if it is I here it should be 4 minus I. Now you look at these two formulas. Okay, we clearly see that there is a general pattern, and the general pattern is now apparent from these formulas. If we have a general positive integer, n is any positive integer, then a plus b whole to the power n equals summation I, which varies from 0 to n. You see, we had 4 here, 3 here, so it will go from 0 to n. nci, a to the power n minus I, b to the power I. Okay, so this expansion is called the binomial formula. But this is only my guess. Okay, at present this is only a guess, because based on what we have got so far, only for till the fifth power we are writing this. We don't yet know whether it is true in general. We have to prove that it is true, and the theorem that proves this, that is called the binomial theorem, and this is the binomial formula. I think I am running out of ink. Let me just quickly refill this. Give me a minute or two. Okay, so now we will try to substantiate our guess. We will now try to prove this. Now in this proof you can see there is a variable positive integer n, and whenever we have a statement that involves n, you know how to prove it using mathematical induction. Then also I said mathematical induction is so useful. In many situations without induction we will not have many proofs. Okay. Let us now try to prove this using mathematical induction. And in the course of this proof, we will see that the two properties of binomial coefficients that we proved earlier, one of them will be useful. So let's just go through the proof. So we are trying to prove this, okay? We want to use induction. So this is the proof I am writing. Okay, I am not writing formally again the theorem, and you understand this. Now this is the proof. We apply induction on n. Okay, so when n is equal to 1, a plus b whole to the power n is a plus b to the power 1, which is nothing but a plus b. And what about the right hand side? When we have n equal to 1, whenever you encounter something in mathematics, don't be afraid. You just concentrate on what is happening right now. Whatever is there, although sometimes it may look complicated, but you write whatever is there as it is and just concentrate on this n. So we write I equal to 0, we write NCI, or in place of n actually I should write 1. So that is the one thing that I am changing here. In place of n I am writing 1, everything else is kept same. 1ci a to the power 1 minus I. Now in these trivial cases means cases which are extremely simple, the simplest cases. It may be tempting to skip some steps and straight away try to write what is going to happen to this thing, okay? But that is most often the situation where people make mistakes. First you write everything clearly, then you do the calculation. Okay, now so what is the meaning of this? First I will put I equal to 0 and write a term. Then plus I put I equal to 1, then write the term. So this becomes 1c0 a to the power 1 minus 0 b to the power 0 plus 1c1, now I am writing I equal to 1, a to the power 1 minus 1 times b to the power 1. Why is it that important that I stick to the form of this formula? It is because I am verifying something, okay? So if I make a mistake here, everything will go haywire. Now 1c0, if you recall, 1c0 is 1. So a to the power 1 minus 0 is a, b to the power 0 becomes 1. So this is a plus 1c1 is also equal to 1. A to the power 1 minus 1 is a to the power 0, which is 1. B to the power 1 is b. So here these two are matching. Hence the formula, that supposed formula, is true for n equal to 1. So for n equal to 1, we have the formula is true. This is the basis for our induction. Not writing all the things in detail, this is the basis for our induction. Now we make the induction assumption or induction hypothesis. So our induction hypothesis is this. Induction hypothesis is the statement that this theorem is true for some positive integer n. Okay, so it is nothing but this itself. A plus b whole to the power n equal to summation I varying from 0 to n nci a to the power n minus I times b to the power I for some n. Not any fixed n, but for a general arbitrary n, but not for all n. That's what we are proving, okay? For some positive integer n. We now have to prove the formula when we have n plus 1 in place of n. So if we put n plus 1 here and n plus 1 here, these two sides should match. Then the induction will be complete. So that's what we will try to do now. Okay. So we start with the left hand side. A plus b whole to the power n. Okay. Now, n plus 1. We are considering the case where we have n plus 1 in place of n. So this product can be written as a plus b times a plus b whole to the power n. This is this calculation is exactly what we did in the case where we found a plus b to the power 5. There we wrote a plus b times a plus b to the power 4, and then we used the expansion for the 4th power to find the expansion for the 5th power. In this case, the expansion for the nth power is given to us. That is the induction hypothesis. So we are going to make use of this. Okay, that's what we are going to do here. A plus b times summation nci a to the power n minus I, b to the power I, and this is varying from 0 to n. Okay. For safety, I am writing this within brackets. Now what I do, I first multiply this product, this sum by a, then plus by b, same usual technique. Using the distributive law that is available in the real number system, I write this as summation. This itself is a sum. Okay. So if I am multiplying this sum by a, every term will be multiplied by a. So here the exponent of a will increase by 1 because I am multiplying by an extra a. Everything else remains the same. So nci a to the power n minus I plus 1 times b to the power I plus summation. Now I am multiplying the sum by b. So the exponent of b will increase by 1. I equal to 0 to n nci a to the power n minus I times b to the power I plus 1. Okay, so I get this sum of two sums. Right. Now next what I do, if I put I equal to 0, okay, let me just put I equal to 0. You see, if we expand this sum, if we write this sum fully, the first term will be obtained when we put I equal to 0. After that, the other terms will come. So I can write this sum like this. nc0 times a to the power n plus 1, because I am putting I equal to 0, and b to the power 0 is b. So this is the first term of this sum. What about the other terms? The other terms I am not writing as a full sum, but writing using this summation notation. So here I am writing I is equal to 1. Now it will start from 1 to n nci a to the power n minus I plus 1 times b to the power I. So I have written this sum as its first term plus the rest of the terms. The rest of the terms are written as another sum, where the index is, okay, by the way, this variable which is changing in the terms, that is called index of the summation. Okay, I forgot to mention that. Anyway, so this part is this sum plus, what do I will do something similar with the second sum. But here what I do, I take the last term of this sum and write it separately. The other terms are written as a sum itself. So here I write I equal to 0 to n minus 1. Okay, because if I put n, I get the last term. So I don't go till n, I stop short of n. nci a to the power n minus I times b to the power I plus 1 plus. Okay, to avoid confusion, let me write it in brackets. The last term here will be obtained by putting I equal to n. So ncn. Here if I put I equal to n, a to the power 0 will not be there, or will be there but it's 1. So b to the power n plus 1. Okay, now I have to continue from here. Okay, so what is the benefit of doing this? Let us try to see. nc0 is 1, so this is nothing but a to the power n plus 1. Okay, plus summation I equal to 1 to n, right? nci a to the power n minus 1 plus, okay, let me write this as n plus 1 minus the same thing, b to the power I. Now I will change this summation. Okay, I will change the index of this summation. Now this part needs some explanation. If I just simply change it, that may be confusing. You see, what is given here, I digress a little bit. Okay, I take a small example and see what happens with this sum and exactly what do I mean by I want to change this sum. Let me take a particular value of n. Let me take say n equal to 3. Then what is this sum? Summation I varying from 0 to 3 minus 1 is 2 nci a to the power n minus I b to the power I plus 1. So what we do, we decide to write this as a sum itself in the expanded fashion. So, I have taken n equal to 3, right? I can write n, I have to write n equal to 3 in these places. So this is 3c0 a cube, but you see here it is different. Okay, it's not b to the power I, b to the power I plus 1. So 0 plus 1 is b. So 3c0 a cube b plus 3c1, since its I is increasing, this is decreasing, a square b square plus 3c2 a b cube plus, till that only I can write, right? I equal to 0, 1 and 2. So this is the sum. Okay. Now I want to change this sum I said, but in exactly what way am I changing this sum? If instead of I varying from 0 to 2, I write I varies from 1 to 3. Okay. If I am saying I is varying from 1 to 3, you see here, since we have I plus 1, here we have 1, 2 and 3. If I am deciding to consider this indices of b or the exponents of b as my index of summation, then I varies from 1 to 3. But what about the other numbers? You see, this is 1 less than the exponent. That means this is 3c, not I anymore, but I minus 1. If I put I equal to 1 here, I will get 3c0. When I put I equal to 2, I get 3c1. I put I equal to 3, I get 3c2. Okay. Now what happens to this 3, 2, 1? If you look carefully, this will be a to the power n plus 1 minus I. Oh, sorry, 3 plus 1 minus I. 3 plus 1 minus I, or yeah, 3 plus 1 minus I. Okay, let us see if we have written the correct thing. When I put I equal to 1, I get a cube. So I get this one. When I put I equal to 2, then I get, see, 1 minus 2 is minus 1, 3 minus 1 is 2, so I get a equal a square. When I put I equal to 3, then these two cancel out. I am left with a to the power 1, so I have this. So this sum is the same as this sum. Do you see the difference? I mean, difference in representation. Their values are same, but they look different. Where is the difference? Here in the limits of these indices. Here it is going from 0 to 2, here it is going from 1 to 3. They are increased by 1. Accordingly, some changes have been made in these exponents. Previously we had 3 minus I and I plus 1. Now we have 3 minus I plus 1. We have added a 1 here and we have subtracted a 1 from here. B to the power I in place of B to the power I plus 1. So that's what I mean by changing the sum, this sum. Okay, so this I will do now with the general sum. So instead of this sum, now I write plus summation. Remember, I am increasing the indices by 1. So I will now vary from 1 to n. In place of NCI, I will have NCI minus 1. You remember this calculation, okay, which was here. A to the power, the exponent of A will be increased by 1 and the exponent of B will be decreased by 1. So A to the power n plus 1 minus I. I have added a 1 and I am subtracting a 1 from here. B to the power I. Okay. So this sum and this sum, they are one and the same. And the last term NCN becomes 1 again. Okay, you can calculate B to the power n plus 1. Now this is where the formula that we have proved previously that involved these NCIs will now be used. You see, it's a sum of two sums where the indices are the same. Their variations are the same. They are changing from 1 to n, right? So if I, in place of these two sums, I can write a single sum where what am I doing? Let me just show you like this. Suppose the first sum is, it looks like this, a1 plus a2 etc plus an. Okay, and the second sum looks like this, plus b1 plus b2 etc plus bn. Of course I can write this expression as a1 plus b1 plus a2 plus b2 plus etc plus an plus bn. I intend to write the terms with same index together. This I can do using the commutative and associative law of ordinary addition. I can rearrange the sum like this. So that's what I am going to do here. Instead of writing two sums, I am writing a single sum where the index is still varying from 1 to n. See, this is the reason why we changed the index here, so that we can see that these two sums are varying over the same values of the indices. This plus this, okay, just like ai plus bi. This plus this, but you can see here that a to the power n plus 1 minus I, b to the power I, we have the same things here. So when we write this plus this, forget the summation, just this plus this, we can take this part common out and we can write nci plus nci minus 1 times a to the power n plus 1 minus I times b to the power I plus b to the power n plus 1. Okay. So we have reached till this. Now after this, here this is the place where we need that formula for binomial coefficients, I mean the combinations. If you recall the formula, we had something like this: NCR plus NC R minus 1 equal to N plus 1 C R. We have in fact proved this. Okay, we have proved this formula. But that's, you see the same pattern is seen here. NCI, in place of R we now have I. So how can I write this? A to the power n plus 1 plus summation I is varying from 1 to n. The other things will stay the same. Now in place of this sum, I can write n plus 1 C I times a to the power n plus 1 minus I times b to the power I plus b to the power n plus 1. Okay. So using this formula that we have already proved before, I am writing it here. Now here you can see that we can write we have 1. Here also we have 1. So these ones can be written as n plus 1 C0 times a to the power n plus 1 minus 0 times b to the power 0. The first term I have written in a somewhat different manner, plus summation I varying from 1 to n plus 1 C I a to the power n plus 1 minus I b to the power I. Now I am making the pattern more apparent. Here in place of 1 I can write n plus 1 C n plus 1. A to the power n plus 1 minus n plus 1, because there is no a, times b to the power n plus 1. Now you look at this final expression and tell me, of course you cannot tell me, but just think of it. This final expression is the same as this sum, where I is varying from 0 to n plus 1, n plus 1 C0, a to the power n plus 1 minus, n plus 1 C I, this times b to the power I. You see, when I write here, of course I have n varying from 1 to n, but we have two extra terms outside this sum. When I put I equal to 0 here, I get n plus 1 C0, a to the power n plus 1 minus 0, b to the power 0. So this term can be taken inside the summation by changing the index to vary not from 1 but from 0. And also, instead of making it go till n, I make it go one step more, n plus 1. If I put n plus 1 in place of I get n plus 1 C n plus 1 times a to the power n plus 1 minus n plus 1 times b to the power n plus 1. So the two extra terms can be taken inside, can be accommodated inside a new sum. of which this sum is a part. And now you look at the binomial formula, the one that we were trying to prove, and see that this is just that formula when in place of n we have n plus 1. That means this is the end of our induction, and we have in fact proved the formula. So this is the binomial theorem, and this theorem actually, although we have stated it only for real numbers, but they are the theorem is true for much more general systems. We will come across them. Okay, you can think of complex numbers in place of real numbers, but those things will come in future. In fact, this is also true in the very general setting of commutative rings, but that is thinking of far future. I mean, the rate at which we are going, it will be quite some time before we get to those things. Okay, so now we have established the formula. A plus b whole to the power n is equal to this nci a to the power n minus I b to the power I, where I is varying from 0 to n. Here n is a positive integer and a and b are real numbers. This is good enough for us for now. Okay, we will extend this formula in future. Now, there are some things to be noted about this formula and the expansions in general. So we are now going to see those things.